Hi class! Today we're going to be looking at exponential functions as part of our functions unit. Alright, so we know that an exponent is when we raise a value to a power. And that value that's raised is called the base. We take some base and then we raise it to an exponent. Like if we did 2 to the third. My base is 2, my exponent is 3. So when we evaluate exponentials, we'll be given some function where x is the exponent. For example, let's take a look at, let's say f of x is equal to 3 to the x plus 5. And let's evaluate it for f of 6. All right, well, I'm going to plug this in where x is. So 3 to the 6th plus 5. Grab my graphing device. See if I can get you to see the screen. There we go. So 3 to the 6th plus 5 is 734. All right. I would like you now to evaluate f of 0 and f of negative 2. Feel free to pause this video while you do that. All right, let's take a look now at exponential form. The form that an exponential equation will take is f of x is equal to k times a to the x plus c. Now, a must be a positive rational number, a must not equal 1, and k must not equal 0. Now, k is some number that we multiply by the base. The base is a, the exponent is x, and then c is going to tell us how that moves up and down. Let's take a look at f of x equals 3 to the x. I'm just going to make a quick xy table with negative 2, negative 1, 0, 1, and 2. All right, this is x and f of x. All right, 3 to the negative 2 equals 1/3 squared, which is 1/9. 3 to the negative 1 equals 1/3 to the power of 1, which is 1/3. 3 to the 0 is 1, because anything to the 0 is 1. 3 to the power of 1 is 3. And 3 squared is 9. Let's take a look at what that looks like on a graph. I'm just quickly going to sketch something out here. Negative 1, negative 2, positive 1, positive 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So negative 2 is going to be at 1/9. Negative 1 will be at 1/3. 0 will be at 1. 1 will be at 3. And 2 will be all the way up here at 9. So you can see that we have a function that looks like this. Now this is what we call an increasing function. Constantly increasing. It's like if we took a little man and put him all the way on the left, if he started walking, would he be going up or down? Well, he'd be going straight up. So increasing the whole way. You'll also see that he never drops below the horizon. And that's because we have a horizontal asymptote. And the rule is that the horizontal asymptote occurs at y equals c. For the y-intercept, that's always going to be found at 0, k plus c. So let's look here. What is c? Well, there's nothing there, so c must be 0. See how my horizontal asymptote is at 0? Now, what about my y-intercept? 0, and now I've got to do k plus c. Well, I don't see a c, so that's 0. What is k? Well, my base is 3. If there's nothing written in front of it, I assume that k is 1. So 1 plus 0 is 1, and yes, that is my y-intercept. Now, what would happen if instead of using an integer, if I used a positive rational number that wasn't an integer? Let's take a look. All right, well, I already know that my horizontal asymptote will be 0 because c is 0, and that my y-intercept will be 1 because this is 1 plus 0. Horizontal asymptote, whoops, y equals 0, and my y-intercept occurs at 0, 1. Again, I'm going to do a little table to help me out. X and f of x with -2, -1, 0, 1, and 2. All right. 1/2 to the -2 is equal to 2 squared, which is 4. 1/2 to the -1 is 2 to the 1, which is 2. 1/2 to the 0 is 1 because anything to the 0 is 1. 1/2 to the power of 1 is just 1/2. And then 1/2 squared, I square the top and bottom numbers, I get 1/4. Let's graph. -1, -2, +1, +2, 1, 2, 3, 4. So at -2, my function is at 4. At -1, it's at 2. At 0, it's at 1. We knew that would happen. At 1, it's at half. At 2, it's at 1/4. And so we see that this one goes like this. Now this one was increasing. If I put that little man to the left, he'll be going downhill. This is a decreasing function. So we can have a little rule about how if a is greater than or equal to, if it's greater than 1, then my function will be increasing. However, if it's between 0 and 1, my function will be decreasing. So, make myself a little asterisk here and write that down. Remember, don't put equal signs because a cannot equal 1. All right. What we're going to do now is I'm going to have you do a little bit of practice by sketching f of x equals 2 to the x plus 3, f of x equals 3 times 1/2 to the x minus 4. So I want you to go ahead and graph those. Just sketch it out here on your paper. And tell me, so you're going to sketch. Find me the values of k and c. Find me the y-intercept. And find me the horizontal asymptote. You can go ahead and pause the video now to do that, and you'll be able to check your answer with the notes key online. Okay, let's talk about exponential growth. Exponential growth is what we can use to help predict how things are going to progress in the future. For example, I might have the diameter of a pumpkin plant. That increases according to the equation L equals 4 times 1.2 to the t, where t is time in days. All right, so let's see. Time and the diameter at 0, 2 days, 4 days, 6 days, 8 days, 10 days, 12 days, 14 days, and 16 days. What is the diameter of the pumpkin? All right, and I'll just come in here and I'll say 4 times 1.2 to the what? To the 0. That's 4. So when I first start measuring, it's at 4. Then I'm going to check it for 2. 5.76. And then 4, 8.29, etc. All right. From there, I can draw a graph. I can take a look at how long the plant is when t is 0. I can also see where it will be in time beyond this. So, what if I wanted to know what will the diameter be in 3 weeks? Well, 3 weeks is 21 days. Do not put a 3 in here. It will give you 3 days. So 4 times 1.2 to the 21. I have 184.02. And that is in centimeters. So prediction is absolutely one way that we can use an exponential equation, predicting exponential growth. All right. Another thing that we can do is we can use exponential functions for financial equations. So the big one we want is the future value of an investment with compound interest. All right. That is FV, or future value, equals PV times 1 plus R over 100 to the Kn. Let's define what all of this is. So we've already said that FV is the future value. PV is the present value. R is the interest rate per year, not per month, not per week, per year. So you may have to do some sort of conversion factor there depending on the problem. K is the number of compounding periods per annum, or per year. And then N is the number of years. All right. So if interest is compounded annually, then K would equal 1. If interest is compounded semi-annually, K is 2. If interest is compounded quarterly, K is 4. And if interest is compounded monthly, then K equals 12, because we're compounding 12 times per year. Okay, let's try a problem. So if we invest 4,000 Malaysian ringgits at 5% per annum, compounded quarterly. All right. After 6 years, how much do we have? All right. Well, let's see. My present value is that 4,000 that was initially put into the bank. 1 plus my rate is 5 over 100 to the k. Well, it's quarterly, so that's 4, and after 6 years. All right. So 4,000 times 1 plus 5 over 100 to the 4 times 6, which is 24. All right. So after 6 years, that has grown to 12,900 ringgits. That's pretty good. Now, there's a way to do this in your calculator. All right? We can go into apps, and I believe all of you have the finance app, and we want to go into TVM Solver. All right? So here, N is the number of payment periods. I% is the annual interest rate. PV is the present value. PMT is the payment amount, where we use negative numbers for money coming out and positive money for numbers coming in. FV is future value. PY is the number of payments per year. CY is the number of compounding periods per year. And payment end begin is used to indicate if the payments are due at the end of the month or at the beginning of the month. All right. I hope that this has been helpful, and you will find in Schoology an assignment for some bookwork.